Hey Joao, can you hear me?
Yeah, I can.
Cool. I'm going to come out of it now, but you're probably going to have to record it from your computer.
That's okay.
Cool. All right. Speak soon.
Wait. I can't
Yeah.
turn on the video.
Oh, can you not? Hold on. Should be able to. Oh wait, that's why. Make host. Change host.
Yay. Okay, I can start the video. Cool.
Cool.
Thank you, Sophie.
No worries.
Should be recording. And I can start with the presentation. So this paper, the faster RCNN towards real-time object detection with region proposal networks, it's a paper from 2015, and it is the paper that allowed for the first time real-time object detection, which is very important. You probably know that nowadays there is a well-known framework called YOLO, which I think it stands for You Only Look Once. That is can give you tens of frames per second with very good quality object detection. And actually YOLO originated from this paper. So this paper is the basis to the real-time implementations. Before this paper, they realized that you can separate object detection in two parts. The first part is the image classification, so the typical problem, for instance, for CIFAR-10, etc. You have a certain image, you want to tell which object is in the image, but the second part, and actually the hard part from object detection, is to create an hypothesis of what parts of the images could be objects. And in the papers that came before this one, they also realized that this region proposal was taking most of the time. I think the RCNN paper, the original RCNN paper, took 40 something seconds to detect objects in an image. The fast RCNN, which is the paper before this one, took, if I'm not mistaken, about 3 seconds. And this paper can get you around 5 frames per second or 0.2 seconds per image using a complex neural network. So how did they do it? So they realized that the problem is in the generating the hypothesis. And in the previous paper, the fast RCNN, that hypothesis generation was implemented on the CPU, while the object detection part was implemented on the GPU. So they thought they could get a quick win just by changing that detection from the CPU from the CPU to the GPU. However, as they write in the paper, there were already a few papers doing this by then, and they didn't have that great results. And why? And what did they do about it? So they realized that actually detecting objects in an image and then classifying those objects are similar tasks. So probably you can share most of the weights in the neural network. And by sharing the weights, not only you get joint optimization, which is better for the end results, but also you can share the computations during the inference, which speeds up the process a lot, as we will see. So this is the faster RCNN paper in a nutshell. The problem, they were trying to detect objects on the CPU. Now they are doing it on the GPU, and they are sharing the method that detects the object with the method that classifies the detected object. So this paper is pretty much all about the region proposal networks, which is the part of the whole system that detects where the objects are. And in the first section, the first and second section actually, they talk about what was being done in the past. And they first say, and with support of figure 1, that there was a significant problem with trying to detect the object, which was the other methods required you to have multiple scales of the same image, or to have multiple filter sizes for that image. So you need to run whatever method you were using, you need to run it multiple times for the same image, which is a bit inconvenient. So in the thing they propose, and I'll talk about it more in a few minutes, they also do multiple sizes, but they do it in a single pass. So you don't need to repeat the same image over and over again. They do it in a single pass. They also evaluate their results in a dataset called Pascal, which maybe I can show you a few examples. At the bottom, this is not the dataset, these are results, but the images are like this. So you have an image that is quite small, usually 600 by 400 pixels, but the size can vary. And the image can contain one or more objects, and those objects can belong to a total of 20 different classes. So in terms of classification of the images, it's not a difficult problem. It's not Sci-Fi 100. You have 20 classes and you have high-ish resolution images. So the detection part is not the difficult part of the problem. The difficult part of the problem is creating the object hypothesis. So then you can place on the image. So let's talk about the paper itself. They also talk about what led us to propose this whole scheme. They didn't come up with the idea out of the blue. It was an iterative process from other authors. And they took the ideas together and created this beautiful paper. And if you look at it, it has 20,000 citations, which is a very significant number. And I believe the paper deserves those citations. So in a nutshell, the system is as depicted in figure 2. So you have a certain image, then you have some convolutional layers, and after those convolutional layers, you have feature maps. From these feature maps, first, you use the region proposal network, which is the main novelty of this paper, to detect which part of the images may be objects. You don't care which type of objects are in the image at this stage. You just care where are the objects and whether they could be objects or if they are just background. After you get the proposals, you use the same feature maps that you have computed before. So there is no computation of the feature maps from scratch from the image. So you take the feature maps and the proposals and you run classification for each proposal. And then you put the results on top of the image and you get those pretty bounding boxes. So this region proposal network simultaneously tries to get the perfect bounding box and just bounding boxes where there are objects. So they don't want many fake bounding boxes. And the paper is this in a nutshell. So it's very easy to explain. I explained most of the paper in 10 minutes, but the devil is in the details. It's not trivial to train this whole thing. They claim in a footnote that, so this paper was accepted to NeurIPS, but I'm showing you the archive version, which is updated after the NeurIPS. And in the archive version of the paper, they say that they can train this whole thing jointly, which is slightly faster compared to what they proposed here in the paper. In the paper, they actually proposed to train these two stages, so the region proposal and the image detection from the proposals, alternatively. So for a certain image, and I'll describe the process with some more detail in a few minutes, but for a certain image, they first train the proposal network, and then they train the detection network, and they interleave these two stages. Since they are sharing the convolutional layers, you can actually share a lot of information between these two stages of training, which results in the good performance results in the results section. So what is important about this region proposal network, which is the core of the paper? First, maybe with the help of an image, it's easier to explain. So they are assuming now that we are working on the feature maps, not on the raw image. Please take into account that whatever numbers they show, they are relative to the feature maps. So they start with a feature map, which are multiple 2D inputs, if I'm not mistaken, and they take a sliding window of 3 by 3. It's not 3 by 3 pixels. It's a sliding window of 3 by 3 on the feature maps. Depending on the underlying image classification architecture they use, they show that this 3 by 3 corresponds to 171 by 171 pixels in ZF, or 228 by 228 image pixels in VGG. So this actually is a significant area. So they do a sliding window over the image, and with that sliding window, they want to answer two questions. Question number one, is there an object here? And question number two, if there is an object here, what is the bounding box for that image? And this is roughly what they are trying to show on the left of image 3. So so this sliding window, as the word sliding window suggests, means that they share the same parameters, the same neural network parameters as they are sliding the window. So this is a very efficient network in terms of number of parameters. This is as opposed to the previous proposals to solve this problem, where when they use neural networks, they needed at least one order of magnitude more parameters. For each point on the sliding window, they convert it into a 256 dimensional fully connected layer. And then they try to solve the two problems: the classification problem, is there an image here or not, and the coordinates problem, so try to define the bounding box. But by this point, you have noticed that they have these anchor boxes on the right, and they have this K here, which is the same K as the number of bounding boxes. What they mean by this is that for each point in the sliding window, they define K boxes. In this case, they use K equals 9. And so they have 9 anchor boxes, and these 9 anchor boxes correspond to 2 dimensions. So on one dimension, they change the size of the anchor box, and in other dimension, they change the aspect ratio of the anchor box. So you can have tall rectangles or wide rectangles. They only consider rectangular shapes in this paper, and at least I don't know much about this subject, but I never saw other shape besides rectangles. So one important detail here is that for each bounding box, they have a neural network at this stage. So these intermediary steps, they do not share weights among different anchor boxes. However, for a certain anchor box, as it slides through the feature map, it preserves the parameters because it is a sliding window. So again, for each anchor box, they convert the feature maps, not the raw input, the feature maps into a certain fully connected layer. In this case, with 256 inputs for the, if you read the paper, you'll see this number is relative to the ZF architecture, not to the VGG. The VGG is larger in general. But then they transform this input into a classification problem and into a regression problem that is jointly solved. So they want to simultaneously tell if this region with this bounding box could have an object, and if it has an object, what is the size of the bounding box? This is a very flexible architecture in the sense that there is a hand raised. Let me see if I can give permission to, or maybe not. I don't see the hand anymore. Again, if you have questions or comments, please add them. Allowed to talk. Hi, Burak, you are now allowed to speak if you unmute your microphone. Not successful. Okay. If you are having problems with the sound, maybe type down the question or the comment. Meanwhile, I'll carry on with the presentation. Where was I? Oh, so solving this, training this bounding box problem. They jointly optimize the classification and the regression layer. How do they do that? So this leads us to the only equation of this paper, but in a nutshell, they have created a loss function that for P of I, P is the probability of a certain bounding center anchor having an object or not. So it's a binary classification problem. And T is the parameters of the bounding box. So it's the shape and the dimensions of the bounding box. So they created a loss function that simultaneously you want to optimize the error associated with classifying incorrectly the presence of an object, plus if the object does exist in the label, you also want to have a correct bounding box. So if you have a proposal of bounding box that does not correspond to any actual label, this part of the loss will be zero, so you don't care about it. You only care about creating bounding boxes when there is an object in practice. These NCLS and REG are regularizing parameters. They hard-coded them in the paper, but they say they don't make that much difference in practice. This lambda is a parameter that balances the weight of these two loss subsections. And they say they define it lambda such as the two loss parts are at similar levels. I think now we have chat. Are those K anchor boxes confined to the size of the 3x3 sliding window, or can they be larger than the sliding window? From what I've read in the paper, I think they can be larger than the sliding window, because here they say that this is a 3x3, and in this paragraph they say that this 3x3 image corresponds to 228 pixels in VGG. But if you look further below, you have boxes with these dimensions, which are much larger than the 3x3 sliding window. So to answer your question, I think that yes, the anchor boxes can be larger. Furthermore, because they have the regression layer, they want to optimize the size of the bounding box. They do not limit the size of the bounding boxes to be within the sliding window. So you can increase your box or decrease your box as you wish. The only restriction that they placed, and they explain that in the results section, is that you don't want boxes that go beyond the size of the image, because that creates errors that are very hard to correct. So in practice, they clip the bounding boxes to the size of the image. We also have another question from Arvid. If the sliding window overlap, could the same object be detected twice by neighboring windows? How is that dealt with? That is a very good question. And in practice, yes, you can detect the same object many, many times, not just because the sliding windows can overlap, but also because you can use you use multiple anchors in the same position of the sliding window. So in practice, you could be detecting the same object many times. To answer your question, I'm not sure if I just don't remember or if they don't talk about it in the paper, but I don't know the answer to that question. So how do they deal with this problem? I believe that they, if they have multiple hypotheses for the same object, they use the bounding boxes that have the highest score in this classifier network, but I'm not sure. And if anyone knows,
I
maybe?
think you're right, and I think they use a non-maximum suppression algorithm in order to filter those boxes, if I'm not mistaken.
I recall reading something about that.
Based on the intersection over union score, which is the basic thing they measure in object detection.
Yeah, but they also use that for generating the hypothesis, right?
Yeah, but they threshold it differently from what I've understood. At this stage, they have something like 0.5 for detecting the foreground, and under 0.1, or if they overlap with the ground truth, they are considered background.
Okay, I hope that answers your question, Arvid. Continuing with the presentation, where was I? Loss function. Okay, so I've explained how the loss function works. Now, in my opinion, the trickiest part of the paper, which is how to generate the labels so you can apply these loss function. So remember, you have two parts of the loss function. The first part is a simple classification network where you want to detect whether there is an object or not in the anchor that you are training on. And the second part is the dimensions of the bounding box. So first, we need to define what is a positive sample for existence of object or a negative sample for an existence of object. So what they do in practice is the following. They take an image from the Pascal dataset, which is annotated with a bounding box around a correct object. And they run their method to generate hypotheses. And they say that a certain hypothesis is true when the intersection over the union which is a certain metric that they use, is higher than 0.7, or if a certain true object, so an object that is labeled in the data set, does not have any anchor whose intersection over union is higher than 0.7, they also consider that as true. So they consider the least bad example as a true sample. And contrarily, they also define negative samples when a certain anchor has its IOU ratio lower than 0.3 for all ground truth boxes. So pretty much if a certain anchor does not match with any image present labeled in the data set in the certain case you are considering. They also describe further down that if they do this, you'll get many more negative examples than positive examples. So they actually sample from these positive and negative examples so that your data set is balanced. So they try to have as many positive as negative examples. We have another question in the chat, which is, so does it mean that the center of the sliding box is the center of each K anchor box and then they look for the best fit in the box? Yes. From what I gathered, that is what they do in practice. But that begs the question, what if the sliding window is the corner and the anchor box is larger than the sliding window? I don't think they answer this in the paper. But it's safe to assume that the sliding window is the center of the anchor box, and because they crop the exterior of the anchor box as if it's outside the image to the limits of the image, I think it could solve this problem. Carrying on with the presentation. So they get these positive and negative examples, and then they sample them, and from these positive and negative examples, then you can have train your model with the losses function. So remember, this is to train the region proposal networks only. We haven't talked about how to train the rest of the network. This is about region proposals, because remember, this is the hardest part of the object detection, or at least the trickiest part, because if you want to classify a certain image, then you can fall back to the traditional problem. And that is the paper in a nutshell. Let me just check if I have more notes that I forgot to talk about. I think this is the core. So they have many numbers. So all these parameters that I've talked about, they describe them thoroughly in the paper. And they also have a repository if you want to have a look. However, they used Caffe, so no PyTorch, no TensorFlow. This is a very old school implementation. But if you have practical questions, such as the one that Christina asked in the chat, I believe we could get the actual answer from the code, because code never lies. And yeah, so they also explain how to train the whole thing, which is a bit more complicated than what I've said before. It's actually a 4-step thing. So first, they train the region proposal network, ignoring the rest of the problem, taking into account an ImageNet pre-trained model, and then they fine-tune on the region proposals. Then separately, they train the fast RCNN, so the previous paper, on the proposals generated by the region proposal network. By this stage, these two networks are completely separated. The only part that they are together is that the image classification network uses the proposals from the region proposal network. But then they join the two networks during the 3rd step, because so as they say, they use the detector network, which is the actual image classification, to initialize the region proposal network training, where they fix the convolutional layers. And if we go to the image above, we can see that they fix this part of the network using the classifier, and then they retrain the region proposal network. And then they freeze the proposals and train the classifier. So you actually have to do these steps in a sequence so as to get the good results. And as they mentioned, for when they are doing this, they do it after you do the first 2 initial steps where you kind of initialize the 2 networks. Then you need to iterate between the region proposal and the image classification. So in practice, this is a bit painful to train, but fortunately they have the code. So worst case scenario, we can follow exactly what they programmed in the code. They also mentioned that they upscale their images. So they say that the typical Pascal image before resizing is 500 by 375. However, they rescale the image such as the shorter side as 600 pixels. I believe they do this because they have a fixed size for the bounding boxes, and upscaling the image to this minimum threshold makes the thing play better. They also mentioned that the bounding boxes were not carefully chosen for this particular data set, and they are powers of 2, which makes me believe their comment here. And yeah, so they also mentioned that if you consider the size of the image, the sliding window, and the 9 different anchors that they use, for each image, you have about 20,000 anchors. From these 20,000 anchors, they ignore most of them because they cross most of the image boundary. And from these anchors, they do some additional filtering, and they sample, so you can get a balanced data set between training and testing. Getting a balanced data set in what they describe here is very important to get good results. And by now, I think we can talk about the results. So this table corresponds to the previous results, where you get a mean average precision of 59.9. So this is the previous paper. And with the implementation from this paper, you get 78.8 mean average precision. So it's much, much higher. And furthermore, remember that in the previous implementation, each image required about 3 seconds, a little bit less than 3 seconds. But now they can run the whole thing in 5 frames per second. And remember, they are using GPUs from many years ago. So if you were to re-implement this in a recent GPU, you would get much, much better performance. So they have shown in this paper that you can get not only better object detection, but also much faster. And why? You can get the better results because now you are jointly optimizing the bounding boxes and the object detection part. And you can get faster performance because they share most of the computations. You don't need to compute everything from scratch every time you're trying to go through the multiple hypotheses. And this speeds up the process a lot. And the last thing I want to show you is the impact of number of proposals. So they train the network always with 2,000 proposals for each image. Of course, they sample from these 2,000 best proposals, but if you go multiple times through the same image, you'll get most of the proposals. However, at inference time, you can choose how many proposals do you want. And they show here that if you use 300 proposals, which is the number that led to these 5 frames per second, if you use 300 proposals, you'll notice something. So the blue line and the red line corresponds to this paper, and the green line and black line corresponds to the papers from before. And if you use 300 proposals, you cannot get a very high recall of the anchor overlaps. So this method, the main advantage, or what I would consider the main advantage of this method, is that you can work with a much smaller number of proposals and yet obtain as good as the results in the previous paper. So for me, this is the perfect paper. You get better results and you get faster execution, and you have a solid underlying assumption that detecting an image or classifying an image should be a very similar task. Therefore, you can share most of the network. And I believe this is the paper in a nutshell. You have a very lengthy results section. I've went through the highlights, but I encourage you to read the rest. And of course, they have many pretty examples. And this is the paper that actually led to YOLO, which is the most popular framework nowadays. Actually, there is a 4th version of YOLO that was released a few months ago. We also have a question. Why bounding boxes instead of masks over pixels? Is this because of the nature of the available training data? This is a good question because I'm not sure. I believe that the Pascal dataset, is trained with the bounding boxes, but I also think that the Pascal dataset includes image segmentation. So they could do both. Let me see. Yeah, they also have segmentation, but perhaps the segmentation dataset is smaller. So they have 422 images with segmentation, and yeah, they have way more images with bounding boxes. So to answer your question, Alexander, I think that it is because of the availability of data above all. If you have more questions, now is the correct time to ask. Or comments in general.
I have a small question, comment, I guess.
Let me just try to change that because
we have a raised hand from Bob.
Oh.
Sorry, let me carefully change. Damn it. I can change tab now because Zoom.
You can't change tabs.
No, because the Zoom
you can move it down.
Bar.
You can move it, right? If you hover, it becomes...
Okay. Thank you. Okay, so comment, Fahan?
So you said YOLO version 4 was released very recently. Is it the state of the art now?
I think it is the state of the art with respect to frames per second at a decent performance, not the state of the art in terms of quality.
So there are options to get a better, because YOLO is very similar to this work, right?
No,
yes.
No, actually, they have a different. The core difference is the fact that this one does in 2 stages the object detection, and YOLO does it in one single stage, and that makes it much faster, but it loses from its mean average precision.
Yeah. I believe you can take it from the name. Like here you have many proposals. YOLO is you only look once. So you don't have as many proposals, or you have one proposal.
Right.
But YOLO can get you multiple images in a single, multiple objects in a single image, right? How do they do it with a single class?
I think it basically, you have a feature extractor, and then you have a few convolution layers after that feature extraction phase. And then at the end of the convolutions, you have a feature vector that gives you part of the results for bounding boxes, and some of others are corresponded to what sort of object it is. I'm not very sure. I don't want to.
Should we talk about the YOLO in details? But I mean, we had YOLO before, didn't we?
I don't think so.
No, we haven't had YOLO. No.
Bob, okay. I've given you the possibility to talk.
Hi, everyone. I might have been reading the table about the speed performances backwards now that I'm thinking about it. I was going to ask, why was it much faster for VGG versus ZF, since ZF is a more complicated architecture, but if that was frames per second, I'm just getting it backwards then.
I don't...
Speed table, yeah, there we go, 17.
Frames per second.
Oh, no. So yeah, I guess any ideas about why ZF would be, no, it is correct. ZF does a simpler architecture than VGG. I guess that would just possibly be the answer.
Yeah,
for the 3 times difference.
I don't know the exact details from both, to be honest. But from what I got from their text, they refer to ZF multiple times as it's a simpler network. And every time we use VGG, we need more parameters to learn from. So even if these VGG and ZF were the same in terms of complexity, their implementation of the of the object detection is more complex for the VGG. So factoring in the two things, I think it explains the difference.
Okay, great. Thank you.
Thank you, Bob. So if we have no more questions, I'm going to stop sharing the screen and recording. Stop recording.